Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 13, Periodic Motion, Video 5. Today's topic is applications of simple harmonic motion. The objectives are: know that simple harmonic motion can occur in any system in which there is a restoring force, such as Fs equals to negative kx. Understand the motion of an object oscillating on a vertical spring is simple harmonic motion. Understand the motion of an oscillating balance wheel on a watch is simple harmonic motion. Be able to apply the idea of simple harmonic motion to different physics situations. Let's examine a body vibrate on a vertical spring. So when you have a vertical spring that obeys Hooke's law, initially is neither stretched or compressed. So we say the initial equilibrium position is right over here at the bottom of the spring. But if the body is suspended from the spring, you will have a new equilibrium position at the top of this object. This is when the object is in equilibrium. It has mg equals to k delta L. The two forces are balanced, and this becomes a new equilibrium position. If the body is displaced from equilibrium, the net force on the body is proportional to its displacement. Therefore, the oscillations are simple harmonic. Let's see how that happens. So, for example, the body is upward, going up. That means above the equilibrium position. In this position, the force from the spring equals to k times delta x. X is the distance from the top of this body to the original equilibrium position. So that is delta L, the whole thing, minus the displacement x. So the net force, if upward is positive, that's what we get. The net force equals to spring force minus mg, because up is positive, so mg is negative. That gives us negative kx, because k times L equals to mg. So KL and mg cancels, so you'll have left is negative kx. This is the equation for simple harmonic motion. So F equals negative kx even when the body is moving below the equilibrium position. X is displacement from that equilibrium position. To find that position, we can use x naught equals mg over k. If the body is set in vertical motion, it oscillates in simple harmonic motion with the same angular frequency as though it were horizontal. So basically, two are the same thing. You have the same frequency. You have the spring in the horizontal, you pull the mass, you will have the frequency of square root k over m. If you set the spring in the vertical and you put the mass down, you will have the same frequency. So what's different? So the vertical simple harmonic motion doesn't differ in any essential way from the horizontal simple harmonic motion. The only real change is the equilibrium position. So the same idea holds if the body with a weight mg is placed on top of compressible spring. So the body is placed atop the spring. It is in equilibrium when upward force exerted by the compressed spring equals to the body's weight. So this is also simple harmonic motion. We have the same omega. Let's take a look at this example. The shock absorbers in an old car with a mass 1,000 kilograms are completely worn out. When a 980 Newton person climbs slowly into the car, to its center of gravity, the car sinks 2.8 centimeters. So when a car with a person aboard hits a bump, the car starts oscillating up and down in simple harmonic motion. Model the car and the person as a single body on a single spring and find the period and frequency of the oscillation. So in order to do that, first we have to find a spring constant. Spring constant equals to spring force divided by the elongation. Spring force is a person's weight. Elongation is 2.8 centimeters. So we have 3.5 times 10 to the 4 kilograms per second squared. As you may notice, the displacement is negative because it's going downward. So from here, we can figure out t equals to 2 pi m over k. In this case, m is the car and the person, because the question to ask you to model the current person as a single body. So we have to add the mass together. And we have the t equals 1.11 seconds, and we can find the frequency is 1 over t is 0.9 hertz. So persistent oscillation with a period about 1 second makes a very unpleasant ride. So the purpose of shock absorbers is to make such oscillations die out quickly. Angular simple harmonic motion. That's another type of oscillation, also simple harmonic motion. This is which keeps time based on regular oscillations of a balanced wheel initially set in motion by a spring, such as in this diagram. The wheel has a moment of inertia I about its axis of rotation right in the middle. The coil of spring exerts a restoring torque that is proportional to the angular displacement theta from the equilibrium position. So the torque equals negative kappa theta. This is very similar to Fx equals negative Kx. In this equation, torque equals negative kappa theta. Kappa is the constant called the torsion constant. So let's take a look. Torque equals I alpha. I alpha equals negative kappa theta. So we can figure out alpha equals negative kappa divided by I times theta. So what is omega? Omega squared equals to kappa divided by I. So omega equals to square root of kappa over I. From there, we can find the frequency and the period. So the motion of rotational simple harmonic motion is described by this function, theta equals to capital theta times cosine omega t plus phi. Remember that phi is the phase angle, and this capital theta is angular amplitude. Now let's take a look, test your understanding. So a block attached to a hanging ideal spring oscillates up and down with a period of 10 seconds on Earth. If you take the block and the spring to Mars, where the acceleration due to gravity is only about 40% as large as on Earth, what will be the new period of oscillation? Let's take a look at the equation of period. Period equals to 2 pi m over k. So if you take it to Mars, mass is not going to change, spring constant is not going to change. Therefore, the period cannot change, has to be 10 seconds. That's the answer. Thanks for watching. See you next time.